Welcome everyone. Today we will look at the work done by an ideal gas under isothermal processes. To do this, we will first need to identify three parts. The first part is what is an isothermal process? All right. The second part is what is an ideal gas? And the third part is how can we find the work done by an ideal gas? So let me just write work done. For the first question, what is an isothermal process? This term simply means that the temperature is constant. So T is constant. Which makes sense, I hope, because iso kind of means same when we look at the root and thermal. Well, we have thermal energy and all that, so it is related to temperature being constant. An ideal gas is simply a gas that obeys the following equation. PV is equal to nRT. The P here is the pressure. V is the volume. The N, the little n, is the mole number. R is just a constant. It is called the gas constant, and T is the temperature, just like here. This equation, what it means actually to be an ideal gas is that we neglect all intermolecular attractions and the volumes of individual gas particles, but it is chemistry, so for the physics part of it, we will just focus on this equation, and work done by a gas is simply equal to work is equal to pressure times delta V. You could prove this to be true using the real definition of work, which is, of course, F dot X, force times displacement. The dot product of force and displacement, to be specific. Alright, so let's begin. What do we have? We have from the ideal gas equation that PV is equal to nRT. So we can modify it to give us P is equal to nRT divided by the volume. And if we substitute it in this equation, what do we have? But before substituting, we need to write this equation in integral form, in differential form. So I am doing that. The more formal definition of work would be dW, I mean, is equal to P and dV. So if we substitute now here, this red part, we have dW is equal to, instead of P, I am writing nRT over the volume, and we have dV. Now, what could we do to solve for work? Yeah, you guessed it right. We will, of course, take the integral of both sides, right? The integral. Let's start this from, I don't know, let's start this part from 0 up to work. And maybe we are at 10 initial volume and we end at 10 final volume. Alright, so this is what we have. The left part simply gives us W, right, the work. For the right hand side, what should we do? Well, the best way to solve an integral is, even if it is very simple like this one, the best way to solve an integral is to take the constants out of the integral, right? So what are constant? The mole number is constant, so we take it out. The n is out now. R is constant, and this is very important. Since we are dealing with an isothermal process, we just said it right here, this means that the temperature is constant as well. So we can take the T out as well. And now we just have an integral that looks like this. From V initial to V final, 1 over V dV. If you know a little bit of calculus, you know that, let me actually write it here. They say, I don't know, from A to B, 1 over X dx. This is equal to, and this can be proved if you would like, if you guys would like, I can prove this in another video. This is simply equal to ln x with these boundaries. So we will use this, of course. Let's not forget. Oh, actually, we don't need to put a c, right? We don't need a plus c because we have our intervals. My bad. But anyways, so if we use this knowledge that comes from math, we know that we can write it like this: ln v from vf and vi. Now I am going to just plug in our boundaries so that we will have, let's do it like this, minus ln v initial. And I think I proved this in logarithms. If you have a subtraction, I think I proved this for addition, but subtraction is just the opposite of addition. So you guys get the idea. If you have this kind of thing where you are subtracting two logarithms with the same base, what you can do is you can write them as a single logarithm with a division like this. And this is actually gives us the formula for work done by an ideal gas in an isothermal process. I hope that you guys enjoyed this video and learned something. If you have any comments or suggestions, please write them in the comment section. I hope to see you in another video. Until then, take care.